It's okay. The intermediate value theorem. It has two hypotheses. Hypothesis number one, f of x must be continuous. Hypothesis number two, yes, Ricky? Still for 2.5. We haven't moved to 2.6 yet. I wish. I'm slow. So f of x must be continuous on the closed interval a comma b, closed brackets. Condition or hypothesis number two, f of x must change sign on the interval a comma b. Then, by IVT, intermediate value theorem, I know you're not going to like, not everyone will like this. There exists a C in the open interval a comma b such that f of c, let's think for a moment before we decide. So we are dealing with an interval, a comma b. And then, yes?
Sorry, could you read again the last line?
Then, by IVT, the intermediate value theorem, there exists a C in the open interval a comma b such that, this is the fourth symbol that I would like us to use if you want, such that. So here's the interval. I have an interval a comma b. I'm going to draw a picture in a minute. I have an interval a comma b. And the function is continuous on this interval. On one end of the interval is negative, on one and the other end is positive. So at f of a is negative and f of b is positive. What has to happen if the function is continuous? What has to happen? It must cross the x-axis. It cannot jump over the x-axis. Excellent. This is the intermediate value theorem. Let's illustrate with a little picture or graph. Here is the interval a comma b. And let's suppose it's negative on this side and it's positive on this side. So in other words, f of a is negative and f of b is positive. There must be a point C such that f of c is 0. This is just a variation of the intermediate value theorem. The intermediate value theorem is basically discussing between m, lowercase m, and uppercase m. Same thing, exactly the same thing, same idea. So I'd like to illustrate with an example. Use the intermediate, let's say 52, on page 129. Now, before we copy this problem, I have a question for you. Did I start this? I did. I have a question for you, and here's my question. Does the intermediate value theorem give us the solution or the x-intercept? No. It only says there must be one. What is it? In chapter 4, we will be able to determine the solution with as many decimal digits as you want, with as accuracy as you want, with no calculator. Just calculus. Okay, ready? You will be able to solve any equation that you can think of using also the intermediate value theorem. Okay, so one more time, use the intermediate value theorem to show that there is a root. So by root or x-intercept or solution to f of x equals 0. We mean the same thing. So a root of f of x, the x-intercept of f of x, or solution of f of x equals 0, these are all three identical concepts. The root of f of x, the x-intercept of f of x, and solutions to the equation f of x equals 0, same identical concept. And they're giving us in 52 the cube root of x equals 1 minus x. And they're very nice and kind on this problem, and they are giving us the interval. They say 0, 1. So let's go to our calculators, not before we create the function. And you can say which function? I move everything to one side. So this is the cube root of x minus 1 plus x equals 0. This is our f of x. So with a graphing calculator, please, in y equals, put in the function we just created. As you know, for the cube root, you have two options. I am lazy with that math button, so I prefer x raised to which power? Which power is the cube root? Thank you. Minus 1 plus x. He saw my ugly face. He will never forget that the cube root of x is x to 1/3. Okay, so then we go to make sure you have the software goes back to default. So I have to check second and table set. And please make sure that only the independent variable is in the ask mode. I will always have to do this. You will never listen to me. Second and table afterwards. What do I have to plug in? Or, and after that, 0 enter and 1 enter, because that's the given interval. So I see that the function changes sign. At 0 is negative and 1 is positive. Good. So now we have to go back and say, number 1, is this function continuous? The cube root is continuous everywhere. I'm gonna add a theorem just now. The cube root is continuous everywhere. -1, it's a horizontal line, and x is continuous everywhere as being polynomial. So we know now that f of x is continuous, and I am going to quote a theorem. Theorem: any combination, I mean addition, subtraction, multiplication, division, of continuous functions is any combo, addition of continuous functions, subtraction of continuous functions, product, division of continuous functions will always be continuous itself. Very good. So f of x is continuous as addition, subtraction of continuous functions. Furthermore, on the interval 0, 1, but it's everywhere. So I will write on 0, 1, closed interval 0, 1. Part 2, I will write that f of 0 equals -1 and f of 1 equals 1. By IVT, what do we conclude? Exactly, that there exists a C in the open interval 0, 1. Exactly, such that or where f of C is 0. It's guaranteed. So by IVT, there exists a C in the open interval 0, 1, such that f of C is 0. We don't have C. C is not determined with IVT. We can determine it with IVT. So I like to also work on 56. Natural log x equals 3 minus 2x. We had a list of 3 functions last time. I would like to graph them again and add natural log to it. you can say enough of this, I got them, but I would like to graph them one more time. So here's tangent between -5/2 and pi/2, tangent x. The second function is the inverse of this function, still between -5/2 and pi/2, arc tangent x. We also graphed the simplest possible rational function, 1 over x. And now I would like to graph natural log x. And remember this for good, please. Very important function. Here it is. Natural log x, and it crosses at 1, comma 0. So please commit to memory these 4 functions moving forward, please. It's the first time this class we encounter natural log. So this is the first time we graphed it. We have other functions that I have to refresh your memory on, but for now, these 4 are good enough. So what is the first step? In this problem 56, they're not nice enough to give us any interval. One note for you. The interval must be a unit interval. So please don't say that this function has a solution between 0 and 10. That's not a unit interval. You can say between 2 and 3. You can say between -5 and -4. You can say between -1 and 0, but you cannot say between 0 and 10. It has to be a 1 unit length. So what will be the first step that I have to perform here to show that this function, this equation has a solution? First step. Say it again? No. First step. Let's go back to the previous problem. What did we do in the previous problem? First step.
Set it equal to 0.
Of course, I have to create the function. Without creating the function, I have no idea what to plug in the graphing calculator. That's the first step. This, very good. Thank you, Chris. Excellent. F of x. Okay, in step 2, I have to say that f of x is continuous, but I have to find the interval. This is not continuous everywhere. This is, and this is, but this is not continuous everywhere. So I know that I have to look for something to the right-hand side of 0 because this will not exist. So let's put the function in. So in y equals clear, and put in natural log. If you need help with this, please let me know. -3 plus 2x. I have no idea where to start, but I will definitely not start with 0 because natural log is not defined at 0. That's why we graphed it before putting it in. Okay, so let's go to second and table. ln. That's the key. ln. Anyone else? Anyone? Okay, so we go to second and table. And I'm going to start with 1. Move to 2. And I'm happy. Why am I happy? Because between 1 and 2, the function definitely is continuous. So I can write it now on 1 comma 2, closed interval, as a sum difference of continuous functions. And number 3, I would write that f of 1 is, and f of 2 is. F of 1 is, I really don't need to copy the numbers. I can, this is good enough. You do not have to copy those numbers. You only have to check and say f of 1 is less than 0, f of 2 is greater than 0. That's all I care about. And then here's our conclusion. Then, by IVT, the intermediate value theorem, what? There exists a C in the open interval 1, 2, such that. Now you understand that the IVT is not applicable if the function is not continuous. Here's a counterexample, right? So let me give an example for 1 to 2. Here it is. The function is positive at 1 and it's negative at 2. Does it cross the x-axis between 1 and 2? Why? Why? What are the two conditions of the IVT? What is the first one? It's not continuous. It has a jump discontinuity. That's why the theorem is not applicable here. Two conditions. The function must be continuous. It's not continuous. Goodbye. So there is no C that crosses where the function crosses the x-axis. Yes, Vanessa? Yes.
For step number 2, you wrote 1, 2. Where did you get that from? How did we know to use those two, 1 and 2?
Can anyone explain? Why did we use 1 and 2? I just picked some values.
It doesn't matter like what.
It doesn't matter.
Okay.
I have to look for a solution and I have to see where it changes sign. And the interval has to have 1 unit length.
Okay. So it could be like 3, 4, or
Any, as long as it's 1 unit length.
okay.
So it's not always going to be 1, 2.
It just happened for this function.
Oh.
You may even have other solutions. I don't care. The problem was asking us to find one.
And if one value is negative and the next value after that is positive,
Then you found the interval.
okay.
It has to. So the function, if the function starts negative and all of a sudden it becomes positive, it's continuous at each and every point. It cannot jump over 0. It has to cross the x-axis if it's coming from negative and going positive, or vice versa. If it's coming from positive to negative, it cannot jump over 0 because it's continuous. Better? Good. Other questions here? Yes, please, Brandon.
So if they were both negative, then it wouldn't.
I will have to continue
Until
I hit a change of sign. Exactly. So if I have negative, 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 positive, then I stop here. Yes, very good.
Vice versa for if it's positive.
Exactly. That's because I'm looking for a change of sign. Yes.
They're basically just testing 2 unit or like a unit.
I may have to go through 10 points or 20 points. I'm not sure, depending on the function.
Okay.
It happened that I started with 1, and the next one was 2, and that was all I needed. But I may have some work to do because the interval is not given for this problem.
Okay.
For the previous one, it was from 0 to 1, but not for this one. Good. Very good questions. Anything else for me? Anything else? Okay, there is one theorem that I would like to point out in the book. We're not going to use it just yet, so that's why I don't want to bother you with this, but I want you to see it. And nobody can see it. And why is that? Here it is. It's on page 124, and we will talk about it and we will apply it. Why isn't this working? Okay, it's working now. Okay. And can anyone tell us when we use something like this? Because we use it several times. And I pointed out to you and I said it's a very important theorem. We're going to use it over and over, but not just yet. But we did use it. So see this function f of another function? Imagine the square root of x plus 1. And then we took the square root and we put it in front. And actually, we swapped the two operators. We took the square root and put it in front of the limit. Or if you can say we put the limit under the square root. So this is the swapping operators theorem, which we're going to use later. We used it, but we really didn't think about it. But when we're going to use it, we're going to think about it very thoroughly. Okay, so I'm not going to say anything more about this theorem just now. But when its turn comes. Ready? So I like to continue with limits at infinity. So this is section 2.6. And that was my mark. Any questions for me? Okay. 2.6. Limits at infinity. So let's start with the first example. We're going to look at, feel free to choose 141, page 141. I would like to start with a simple one. I'm going to make one up. So limit as x approaches infinity from x squared minus 3x plus 1 divided by negative 2x squared minus 3. Okay. So this entire section, 2.6, talks about what happens to a function, where the function values go as x approaches infinity or negative infinity. Okay? Like before, with all the limits that we looked at, I have to plug it in. How do I plug in infinity? Well, I'm asking myself which of these three terms is the most powerful at infinity. As x increases without bound, which one will dictate? Which one will be the most powerful? Number 1, number 2, or number 3? Of course, x squared is the most powerful. Okay, what about the denominator? As x increases without bound, which of these two is the most powerful? This one, right? So the top one will go to positive infinity. The bottom one will go to good. So the sign is not important. So infinity and infinity. So this is our second situation of indeterminate case. Can anyone remind us what was the first indeterminate case? Excellent. So there are 7 indeterminate cases. We only looked at 0 over 0, and this one is the next one. The sign is not important. So this is an indeterminate case, infinity over infinity. Good. Can anyone give us the degree of the numerator? Very good. If you say 2, you said 2, correct? Then I will factor out x squared. Can anyone give us the degree of the denominator? If you say that, then I will factor out the degree. Now you could say, wait a minute, but x squared is not factorable. It's not the common factor from all these 3. It's not. I will force it out. As long as, how many terms do I have to write here? Yes, because I started with 3, I have to write 3. Correct. So x squared times what will be x squared? Good. Obviously minus. X squared times what is negative 3x? Negative 3 over x. Let's do this together. X squared over 1 times 3 over x. You simplify an x and you get negative 3x. We agree? And then plus x squared times what is 1? Obviously. Excellent. Well done. Excellent. Good job. Same thing for the denominator, please. Negative 2 minus? Very good. Now we stop to make a short discussion, have a short discussion about anything like limit 1 over x as x approaches infinity. Do we remember the graph? A few minutes ago we talked about the graph. Let's look at the graph again. Here it is. So this is a graph of 1 over x. So as x approaches infinity, where will the functions go? Function values go? Exactly. What if I have limit of 1 over x to a power r as x approaches infinity, and r is a positive number, meaning it's not bringing the quantity to the top. Because if it's negative, it's a different story. What will this answer be no matter what? Of course. Do you all see that? In other words, what am I telling you? Is that 1 over x as x approaches infinity is 0. 1 over x squared as x approaches infinity is 1 over x cubed as x approaches infinity is, and so on and so forth. Now 1 over x to negative 3, it's not going to be 0 as x approaches infinity. So that's why we stated this condition. So then we can come back and analyze the situation. Can I simplify x squared with x squared? But what if x is 0? But can it be? Look where we are. It's so far away from 0 that there is no discussion there. Of course I can simplify x squared with x squared. We're so far that way, we can't even see 0. Good. What will you say about this as x approaches infinity? What do you think about this as x approaches infinity? What do you think about this as x approaches infinity? Excellent. And then what will be the final answer? And now I can drop the limit operator. What does this mean about a function? As x approaches infinity, the function values approach negative 1/2. What does this mean? Excellent, Chris. Thank you. So horizontal asymptote. How do I write it? Very good. Awesome. This function, the original function, has a horizontal asymptote. Y equals negative 1/2. And now I have to be exact because I didn't check. Well, in this case, it's not going to make any difference. But you have to be exact and say at infinity. For rational function, it's not going to be an issue. But for other functions, it will be. Is there a possibility that a function has one type or one asymptote to the left and a different one to the right? It can. Of course, not here. But I just want us to get used to it. So this is the concept of limits at infinity. Now, please choose anything you want. And I do have to show something like 26. Yes, please.
So is the horizontal asymptote the only final answer for that question?
No. The answer is negative 1/2.
Yeah, but is that the
So that tells us that there is a horizontal asymptote y equals
so
negative.
that's the final answer.
No, the final answer is negative 1/2. But what we learn about the function in this case is that it has a horizontal asymptote y equals negative 1/2 at infinity. It's an like, for example, what do we? Very good question, actually. So what if I say limit as x approaches 0 from the left of 1 over x is negative infinity? What does this say about function 1 over x? Bless you. This means that, look at the graph. As x approaches 0 from the left, the function values approach negative infinity. What does that mean about the function? It's a vertical asymptote. X equals 0 is a VA. The same way here, when we determine the limit of a function as x approaches infinity or negative infinity, if we get a number, not infinity, negative infinity, or d and e, then we will automatically conclude that the function has a horizontal asymptote y equals negative 1/2 at infinity. The same idea here. Very important too, very important concepts. Are we okay? Yes, questions? Okay, let's look at 26 then, on page 141. Limit as x approaches negative infinity from x plus the square root of x squared plus 2x. And then I would like you to choose any problem you want. I need to show you these two specific ones. Totally different, they're very different. And then we can work on other problems. Okay. So, like before, I have to do what first? For any limit. I do this for every limit at the beginning. Plug it in. Okay. So, when x approaches negative infinity, where does this value go? Do you all agree? Okay, so this approaches negative infinity. Good. So now, which of these two is the most powerful? Okay, done. So when x approaches negative infinity, x squared approaches infinity, and the square root of positive infinity is positive infinity. We go back to, yes?
I missed the part on why x is negative infinity.
When,
Oh, okay, never mind.
Okay, so now this is our third indeterminate case. No one knows what this means, and no one can predict. It can be 5, or it can be D and E. We don't know. So this is our third one, infinity minus infinity, or negative infinity plus infinity, doesn't matter. So you cannot say, oh, negative infinity plus infinity is 0. No. Infinity for you is 10 million. For me is 100 million. We don't know. Good. So I'm trying to find this limit. Let's look at the function, think about it, and say, oh, easy. The limit is not easy overall. It has a lot of steps. But the first step, easy. What do we do? The only thing we can do. Kent? Who said it? Harvey, what did you say? Of course, that's the only way. I don't have anything else. I can add, I can subtract, I can simplify, I can factor, nothing. My only choice, my only hope is to rationalize. Indeed. By what? Excellent. So limit as x approaches negative infinity. Please dictate. I'm going to write the easy one, which is the denominator, of course, because this is over 1. And please give me the numerator. Do not distribute, please. We are way ahead of that.
X minus.
Careful. First term squared minus the second term squared.
So yes.
Very good. Yes, let's put parentheses so that we don't make a mistake.
X squared plus 2.
Very good. Are we okay so far? Yes, everyone? First term squared minus the second term squared. A plus B times A minus B. A plus B times A minus B is A squared minus B squared. Is that better, everyone? Perfect. Okay, I will distribute at the top. So this is limit. As x approaches negative infinity, x squared minus 2x over x minus. Do not continue, just write x minus, and let's talk about the next step. Exactly how we proceeded here before. What is the degree of this polynomial? I will factor out x squared. Not outside of the radical, please. Inside of the radical, I factor out x squared. How many terms? Yes. How many terms we have inside? Oh, go ahead.
2.
Yes. Please tell me what terms I have to write.
1 plus 1 over 2 1 over x. I mean 2 over x.
Perfect. In the meantime, I can cancel these two because one is positive and one is negative. So limit as x approaches negative infinity, the top is negative 2x. I have to stop. I have to copy x. Do not copy anything else. The square root of x squared is our next step. So let's talk about it. I'll come back. The square root of x squared. What do we know about this? Never. It's exactly. It's the absolute value of x. Please be careful. Which means x if x is positive or negative x if x is negative. Very careful. So knowing that, please tell me, what do I replace the square root of x squared by? Because I can take the square root from it. So this, maybe I should write it for everyone. Let me write it one more step, like this first, for everyone to see. We are allowed to separate the radical if it's a product under the radical. Simple. Okay, and now, please tell me, what do we replace this by? When I write it one more time, do I replace it by positive x or do I replace it by negative x? That's the key. Why negative? Because x approaches negative infinity. Awesome. Well done. So then, we have limit as x approaches negative infinity, negative 2x. Can anyone dictate the denominator? That's why we separate and we took it slowly, and we have to do what? Very good. Okay. Almost there. What do you think I'm going to do now to the denominator?
Combine the terms.
Can't, because it's multiplied by the square root.
Like 2x.
I can't. I can because it's multiplied by, exactly. I will factor out x. So negative 2x, factor out x, and please tell me what is left in parentheses. Exactly, 1 plus. What now? What do you think? Yes, that was the target. So now it's final. After you tell me where this is going, as x approaches infinity, where will 2 over x go? Excellent. So now what is left at the top from the whole thing? Negative 2. What is left in the denominator?
1 plus 2.
Exactly, which is? So the answer is, what do we conclude about this function?
Function values approach
Y equals negative 1.
horizontal.
Horizontal asymptote for sure. Now I know for sure that only at you understand why. We use the fact here to replace the absolute value of x by negative x because x approaches negative infinity. It's guaranteed that this will not be the limit at the other end. And by the way, it doesn't even have a limit at the other end. It's the end. Any questions? This was a long problem. Okay, so please choose. Anything you like from, we have time for one more. From 15 to 38, anything you want. So, on page 141. Yes, which one? Any preference?
Then we do 21.
Which one?
21.
21? Okay, we want to do 21. And 21 has limit as x approaches infinity. 2x squared plus 1 squared over x minus 1 squared x squared plus x. Very good. So the top, where does the top go? Of course. Where does the denominator go? Infinity. Very good. Okay, so when we expand the numerator, what will be the leading term? Just give me the leading term. 4x to the 4th. Okay. And yes, I have plus 2 times the first times the second. And I'm done with the top. When I expand this portion, I will have x squared minus 2x plus 1. And now you could say, well, you're contradicting yourself. You always told us not to multiply the factors in the denominator. Well, look what you're doing. True, but for this limit, I have no choice. I have to multiply the factors in the denominators to see what the leading coefficient is. So x squared times x squared, x to the 4th, x squared times negative 2x, negative 2x to the 3rd, and plus x squared. X times x squared plus x cubed minus 2x squared and plus x. I had no choice. So now, can anyone tell us what is the degree of the top? So which of those 3 terms is the most powerful in this situation? Can anyone tell us what is the degree of the denominator? So which of these 2, 4, 6 terms is the most powerful? What do we know from pre-calculus? When we determine, yes? Will be?
Or the ratio.
Excellent. The ratio of the leading coefficients. Yes. So we don't have to remember that. If you don't remember, that's fine. However, what we need to do is factor out what at the top? What is the degree? Very good. And you'll have 4 plus 4 over x squared plus 1 over x to the 4th. I will combine like terms in the denominator, but I will have to factor out x to the 4th. So I have 1. No, this is just, I'm sorry, this is negative x cubed, right? So negative x, negative 1 over x. And this is minus 1 over x squared and plus 1 over x cubed. What will happen to this, 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 and this? And these go away. And exactly as Chris said, the leading coefficient or the leading coefficient. And what is the answer? The answer is 4, which means y equals 4, horizontal asymptote. It's a rational function. It will be on both sides. But if you want to be safe, you can write at infinity. But it's a rational function. It will definitely be at both sides.